In this video, I'll show you how you can use the central limit theorem and ideas from the normal distribution to solve probability problems. So in this case, it says historically the time it takes a university professor to grade a student assignment is highly skewed with a mean of 8 minutes and a standard deviation of 10 minutes. So perhaps the distribution looks something like this of the population with a mean equal to 8 minutes and a population standard deviation equal to 10 minutes. This term, the professor has 62 students, so that means that n is equal to 62 students. And if we consider these students to be a random sample, which is a whole nother situation in itself, but we won't discuss that now. So if we assume that these students are a random sample, then we should define and draw the distribution of sample means. Well, from the central limit theorem, CLT, we know that x bar, the sample mean, will just be distributed normally with a mean of mu and a standard deviation of sigma over the square root of our sample size. So that's how we can denote it with symbols. What this means to us is that we have a normal distribution that looks like this, that is centered at the population mean, 8 minutes, and then our sigma of x bar is then equal to sigma over the sample size. So we have to account for the sample size. Recall, as n gets larger, the more normal our distribution will be, and the then spread of our distribution will be smaller. And so because our sample size is 62, even though we have a skewed population distribution up here, we know from the central limit theorem that n is large enough, so n is big enough, it's greater than 30 is kind of the rule of thumb, that the sampling distribution of our sample means will still be normal, which is awesome. So here we can put in our sigma, which we know is 10. We have a sample size of 62, so the standard error, or the standard deviation of x bar, is equal to 10 over 62, which is approximately 1.27. So if we draw our distribution just like how we have all along, now that we know that x bar is normally distributed, we can just apply the same things that we did when we were using just regular normal distributions. So we have a mean of 8. One standard deviation up from the mean will be 9.27. 2 standard deviations is 10.54. 3 standard deviations is 11.81. 1 standard deviation down will be 6.73. 2 standard deviations down is 5.46. And 3 standard deviations down is 4.19. So now that we've drawn the distribution of x bar, we can then answer the last problem, which is what is the chance it takes less than 7 minutes on average to grade the student assignments this term? So what that means is what's the likelihood that the sample average will be less than 7? So we're looking at this region. We want to write this in notation. This would be the probability that x bar is less than 7 minutes. Well, we can do this by simply calculating a z-score. So no different than any other normal distribution. We say, okay, well then that's the same as the probability of z being less than my value that I'm curious about, finding the area below, minus my mean, which is 8 minutes, divided by my standard deviation for my statistic, which in this case is 1.27. So this is then equal to the probability that z is less than negative 0.79, and I've rounded it just to 2 decimal places so I can easily find it on the z table. So now I can go over to the z table, and I just want to find the area that falls below the z-score of negative 0.79. So I'm going to find the first root of 0.79, and I know that the very last column is going to be my 0.09. So if I look up just a little bit, I can see that the last column is here, 0.09. So if I come down, I'll scroll across and I see that the proportion that falls below a z-score of negative 0.079 is 0.21476. So this is equal to 0.21476. or there is a 21.5% chance, I just rounded a little bit, that it'll take less than 7 minutes on average to grade the student assignments this term.